So this is kind of the idea of the generator. We could go like this, have the water spilling. You see what we're doing here? So we're first starting with the magnet. Let's say we start, okay, so let's say we start with the north facing the coil. On this one, they don't let you bring it close or far. You just can play with the number of turns. You can play with the area, okay, and you can have the field strength showing. Okay, so now what you can do is you can have water. The water is going to turn this. So you're not really changing so much the field strength itself because you're not bringing the coil close or far. But you're just spinning the B field, you see? So you can just say, turn that on. Let's say instead of the light bulb, we put this on. And now turn this on. And look at what happens. You created AC current. Let's test the field strength. Oops. Ah. And so 2 Gauss, 1 Gauss. Field strength is about 2 Gauss. Okay, so the average field strength is around 2, 1. Okay, it's about 1.5 Gauss. Okay, so now let's make an example out of that. So we have a coil. So the field strength B average is 1.5 Gauss, right? So on this one, what I'm going to do is have the water come this way, and this is going to spin at 100 RPM. So how do we calculate the EMF induced in this case? So I need the radius of the coil. Radius of the coil is going to be, okay, about 2.5 centimeters again. 2.5 centimeters. Okay, so now the field is like this. Okay, so now you have EMF is negative N. In this case, the area is constant, right? Negative NA dB dt. Actually, the B is constant too. But what's changing is the cosine of the angle between them. So, right, remember flux is BA cosine theta. So the A came out, the N came out, and the A came out. The B actually can come out. Oh, that's nice, negative NBA. It's nice that we're talking about this topic this week because the NBA is going to start back up again, right? This Friday. Basketball in Orlando. Can't wait. So it's a nice time for it to come up because we're ending our class. We can finally start watching some basketball. All right, NBA. So next time you see an NBA game, think about number of turns, magnetic field, and the area of the loop. Right? Not basketball. Right? No ha-ha, no, come on. Lol. I want to see some lols, some oofs, some ha-ha. Now, how do we take the derivative of that? Well, theta is equal to omega t. And omega is 2 pi f. right? So that's how we're going to incorporate the derivative. So we're going to say EMF equals negative NBA d by dt cosine of 2 pi ft. Now the derivative of that is going to be, the derivative of cosine is negative sine. So it's just going to be NBA 2 pi f sine of 2 pi ft. So again, the voltage that you create is itself a sinusoidal varying volt, right? Whose maximum value is this. So in our case, in our simulation, we have what? The number of turns is what? 3 turns. Our B is 1.5 Gauss. One and a half times 10 to the minus 4. 1.5 Gauss. Our area is 2 pi. No, sorry, our area is pi times r squared. Our r is 0.025 centimeters. 0.025 centimeters. So the turns, the B field, the area, pi r squared, and then 2 pi. Okay, now what's our frequency? Our frequency is given in units of 100 revs per minute, right? RPM. RPM stands for revolutions per minute. So to change that to frequency of the usual metric unit of frequency is cycles per second. Well, 1 revolution is the same as a cycle. So then we don't have to necessarily change that. But the minute, we can say we can say 1 minute is 60 seconds. So the frequency is, that becomes what? 5/3. 2 goes into there. 5/3 cycles per second. Yeah, so if I have the RPM at 100 RPM, it's 5/3 cycles per second. So we put that one there, 5/3. So let's see what that comes out. Three times 1.5 times pi times 0.025 squared times 2 times pi times 5 divided by 3. It's not that big. I thought it was going to be bigger. 3 times this times 0.04 10 to the minus 4 squared times pi. But then this has a 10 to the minus 4, right? So 0.0925 times 10 to the minus 4. This is 3. 1.5 to the minus 4 pi sine of 2 pi ft. So of course the maximum value is going to be 0.0925 times 10 to the minus 4 volts. Yeah, so it's not that big. But over here, we actually see it. So I'm not really sure what the scale is, but definitely this one is, yeah, it goes all the way to here.